Okay, it's 5 o'clock, so let's get started. Yeah, audio should be working fine. If there's any issues with the audio and you're watching, please let me know. So let me just type that real quick. Okay. Yeah, so the topic for today is publication grade graphics, which I think is one of the real strengths of R. Because, yeah, well, I'm going to show you, of course. But also, the learning curve for R might seem steep at times, but I think for graphics it's really nice. And very quickly you can do things with R that are prohibitively difficult in other software. So, yeah, there's 4 things I want to do today. First, I want to talk about the design principles for scientific figures. Then I want to talk about how you can do that in R, and I'm going to be showing you how you can do it in base R. So that's what we've been using for the cake exercise. But I'll also show you how you can do it in Ggplot2, which is a very popular library for plotting data in R. I think for most beginners, Ggplot2 is easier. So we're going to do the exercise, which is number 4, in Ggplot2. But yeah, I will show you some differences between base and Ggplot, and I don't really think one is better than the other, but we'll get to that. And also something I'm going to share with you, there are a lot of papers, I'm sure you've read some, where the figures are just not really crisp, even though they are high resolution. That has to do with rendering graphics, because you can tell your computer where to draw a line, but once you print it to something that isn't PDF, then there's a limited resolution in Word, in bitmap, in PNG. So yeah, you have to translate that, and you have to apply something like anti-aliasing to prevent lines from being jagged and to prevent text from being very difficult to read. So there are different ways you can do that, and of course it all happens automatically. It's not something that you have to specify, but the default method that's being used in our, at least in RStudio, isn't very good. So I'm going to show you a simple fix using the default device, and I'm also going to show you an alternative, AGG, which is even better. And if you combine the two, you can get really high quality graphics even at lower resolutions. Okay, so yeah, I'll get right to it. Oh yeah, one more thing. I think for today I'm only going to be needing I haven't given this lecture before, so I'm not sure, but I think it will only take about an hour. And the second half of the session today we will use for the exercise. So we can do it here, and I can help you if you get stuck. Also, because the packages we're going to be using today are quite a few, and especially SF for drawing maps can cause some errors sometime. So then we'll have plenty of time to do any kind of troubleshooting. Okay, so first the graphical design principles for scientific figures. I think some really important things include the data to ink ratio. So what that means is very simple, that you should try to maximize the amount of ink used to represent the data with regards to the total ink in the figure. So don't clutter your figure. Don't use more than you need, because the emphasis should be on the data and not on the decorations around it. This is actually a concept by Edward Tufte, who has written a lot of really nice books on visualization of data. So yeah, if you'd like, you can look it up. A lot of it is also online, and he has really nice examples. So what do I mean? Yeah, this is an example of a very poor data to ink ratio, very low data to ink ratio. Can anyone point out the shortcomings of this figure? How could you improve this figure? Yeah, that would be a good start. There's no reason for a dark green background. Yeah? Yeah, very good. So there are cases where color is very helpful, but what's the point of the colors here? They are already separated bars. Anything else? Yeah, there's no point to the legend either, because the categories are already written here, and then again it says there's categories over here. So there's a lot of redundancy going on. There's some decorative elements like the color and the background and the shadow that you really don't need. There's one other difference that I would remove, and that's that don't put units of measurement in the axis ticks because you're going to be reading them over and over and over, and it just makes the plot more crowded. It's much easier to just say these are percentages and only show the numbers. Yeah, so that's I think it's a very simple concept, but a lot of people do it wrong. So try to keep your figures a little bit clean. You can go too far. If you look up data to ink ratio, you see a lot of figures where people even remove the axes and just print the numbers in the bars. Well, that happens to work for a bar chart, but for any other kind of figure, you really shouldn't remove the axes. And I think most scientific journals require both axes to be annotated and to be clear. So the point is not to make it ultra minimalistic. The point is just to not add decorative things to your plot, because that's not the point. You're trying to convey information. So avoid decoration, borders, shadows, and gradients, for example. Write the unit of measurement in the label and not in the ticks. So the tick is the things that you see over here, 1, 2, 3, 4, 5, 6. And the label is what you would print over here, or in this case, it's printed over here. Finally, grid lines. So some software is very happy to add grids to every figure, but often there is no point to a grid. The only reason you would add a grid to your figure is if it is important to read the actual value of the figure. And if you're trying to just show the two groups are different, then what's the point of a grid? You can see that by the difference in height. So the grid is really just adding clutter to your figure. Now, there are, of course, good reasons that you sometimes do want to use a grid. So when you do, a simple design choice is to always use a low contrast grid. So some people are really in favor of dark on white. So this is a white background with dark colored grid. Or you can do the other way around, a dark background with a white grid. Personally, I don't really care. Either is okay as long as you do it in a low contrast, because once you do a higher contrast like this, black and white or dark gray and white, then it really takes away from the things that you're actually trying to show, which in this case would be the 5 data points and maybe the regression line. Okay, then next figure. What's wrong with this figure? Or, okay, I kind of spoiled it, but what do you think of this figure? Is it good? Is it bad? What could you improve? Can't really read the labels. Yeah, it's very crowded. That's one. It might be what you want if all of the labels are indeed important. What else?
There is missing the legend for the colors.
Yeah, there's no legend. That's important because one person might mean that green is positive, the other might mean that it's negative. That's just a choice.
Sorry.
No problem. Anything else?
No information at all. I mean, either find out any magnetically on the line. That can even be.
Yeah, so one thing, of course you could write it in the caption, but you should measure how this was clustered, like what are we looking at. But what I think is a really important issue here is the color used, because 8% of the male population cannot really tell the difference between green and red very well, and also about 1% of female population. That's a very poor choice. Unfortunately, it's very common in heat maps, but it's much better to use a color scheme that you're sure everyone can distinguish the colors. So for example, you could go with this color scheme, which is also popular for heat maps. And red-blue color blindness is exceedingly rare. So this is a much better choice. Okay, so what do you think about this color gradient? Are there any reasons that you would or wouldn't use this? It's called rainbow for, I think, obvious reasons. So what do you think of the rainbow gradient? Too many. Okay, so it's a gradient. It's continuous. So you can have it. Yeah.
It's maybe difficult then to see if you not
Okay, so that's what you mean by too many colors. Yeah, so it's hard to tell whether a value is low or high just by looking. You have to keep referring to the legend. Yeah, that's a good point. Anything else?
The seems like and then I myself have made some problems with colors. Seems that the different colors are also different
Yes,
with
very, very important. So this color scheme is uniformly distributed. So these are all the different wavelengths linearly, one by one. But our eyes don't see every color with the same accuracy. So this is called non-perceptually uniform. And if you stretch out the parts that we are more perceptive to, like this, then you get a color scheme where every color seems to occupy the same width. So that's called perceptual uniformity, and it's really important when your figure is displaying differences over a gradient. So if let's say that this ranges from 0 to 100%, then you want to use a color scheme that's perceptually uniform, because otherwise you are blowing up certain differences. You know, the difference between green and orange may seem really big to us, but actually the distance is not much bigger than the difference between green and more green. So that's a problem. Now, of course, there is another problem here, and that's that, again, we're using the entire spectrum. And there are going to be a lot of people who are not able to tell the differences between all these colors very well. So the bottom gradient is perceptually uniform, but still not colorblind friendly. So there are some alternatives that I'd like to show you. I'll just open these in new tabs. So the first one's called Color Brewer. This is very nice if you have discrete classes. So for the most common example is you're trying to draw a map, but also if you have different bars and you want to show the differences, or if you have 3 groups in a scatter plot that you want to color. These color schemes are maximally separated, so they are the most different colors that you can get under certain restrictions. For example, I only want colorblind safe colors, and then fewer options are left. And I need 6 different classes. And I don't have a sequence, but it has to diverge, it has to go from one to another. So this is a very useful tool. I use it a lot. The only downside is that you can only generate that many colors that are still all distinctly visible if you are using these restrictions like colorblind safe and print friendly, etc. So that is something to consider. And if you're trying to show a gradient, then this is not what you should use. So what can you use? This is called Viridis. That's the top scale over here. This color scale is actually perceptually uniform, as is the second one, Magma. These are all perceptually uniform, but especially the first 2 are really good because they are also colorblind friendly. You can use these. There's a package called Viridis, and you can load it, and you'll have access to the color scale, and we'll see that in the assignment today, how you can use that. So just to show you, here we see the different color schemes that are very commonly used. So rainbow, because it's standard in R. Heat is also standard in R. If you load Ggplot, it will try to color like this. Something interesting about this one. This one is perceptually uniform, but if you compare this to Viridis, you can see that there's a much wider possibility of separation in Viridis because we're using more of the spectrum while still having colorblind friendliness and while still being perceptually uniform. So especially these 2 are really nice. Then over here it shows what they look like to colorblind people. So there are different kinds of color blindness, and you can see that some of these really are not so good. Like rainbow, you can kind of tell low from high, but that's about it, etc. So I will share these links, and you can see what it looks like. Okay, then we have the last one, Ggpsci. This one is interesting because certain journals have a certain color scheme that is already being used in the paper throughout for coloring certain elements. And if you're like, well, I like the aesthetics of this journal, I'm going to publish there, I want to adhere to their color scheme, then you can use this package to access the colors that are used over there. For example, this is the color scheme used in the Lancet and Journal of American Medical Association, etc. So you can you can go with that as well. It's another choice. Okay, so those are some simple improvements over the default color palettes that we have in R. Then, graphical integrity. For this I also want to go to a link to show you. I will share the slides afterwards to make it easier to access them. This is a page that it has a lot of nice information. Some of it is better quality, some of it is not so good quality, but this page is actually pretty good. Here are a lot of examples, so I just want to show a couple of how graphs can be misleading. Because it's really important that your graph actually shows gives an actual representation of what is going on. So the most common problem that you see is that people are comparing bar charts, which shows the height of something, but they cut off the axis without showing it. So over here, they've pressed this really up into the roof, and this one is very low. But yeah, this axis only goes from 420 to 490 million. So the difference is really blown up. And the same over here. This looks like there's a very problematic increase in welfare spending. But yeah, if you look at it, it's really from 94 million to 108 million. That brings it into perspective. So for bar plots specifically, usually shouldn't cut off the axis, so you should just start at 0. If you do want to cut off the axis, then add a break, there's a little zigzag to show that you cut off the axis. This one is also very interesting. This is something you see very common in medical journals, where if I have one quick glance at this figure, well, first off, there's a lot of decoration going on there, which is just distracting you from the actual data. If you read this quickly, how many children do you think suffer from lower leg injuries? Yeah, so it's seen that 1 in 5 children gets lower leg injuries, 1 in 5 children gets thigh bone injuries, but that's not what it shows. Because if you read over here, it says top traumatic orthopedic injuries for which children are hospitalized. So among children which are hospitalized, these are the most common reasons. So we have no idea of the actual occurrence of these injuries. They could be much, much lower. Maybe this is only 1% of all children instead of 21%. So yeah, that's a very misleading way to represent data. It really exaggerates the actual numbers. So if you do want to show your numbers like this, the percentage among a certain specific group which has already been selected, then yeah, what you should do is at least also include the hospitalization rates, because then people in their head can convert it. But even better is just to show the actual percentages and maybe mention this somewhere in the text. There's another cutoff axis that makes no sense. There's a difference between 35 and 40%. What's with this one? Yeah, seems to go up and down a lot, but the axis only shows a very limited range. And over here we have the same issue. And oh yeah, this one also, it starts at 50%. Why does it start at 50%? No idea. Let's see if there were other interesting ones. Yeah, this one is really bad, but not a scientific figure. This is a bit more technical, but these people don't understand what confidence or prediction intervals are. First off, we don't know what this is. Are we looking at a regression line, or are we looking at the actual data? Because if this is the average temperature, then what is this? Is this a confidence interval? So does this show where we expect the average to be? Or is this a prediction interval? Does this show us where we expect the actual values to be? Which is a really big difference. And also, a 95% confidence interval is not 100% confident. So it really means nothing if your values exceed a confidence interval. So yeah, it's just another strange interpretation of data. Over here, this is also very important. these two items, let's see, we have tuition and bachelor degree earnings. Yeah, this is just a gross misrepresentation of data, because tuition you only pay once per year, but you know, once you have a job, hopefully you will get paid every year. So what does this mean? What does it even mean for tuition to be the same as 1 year of salary? Why would that number have to coincide? So it's just, it shows actual data, but these data aren't comparable because they show different timescales. Now then over here, this one is also interesting. Without further context, it's very hard to see why this one is wrong. It shows how often people use their consoles, so gaming consoles, the PlayStation 2, PlayStation 3, the Xbox 360, etc. And yeah, this is supposed to show that nobody uses their Wii, because it only has an average of about 6% use in the last 6 months per the number of people who own a Wii. But it doesn't show how many people own a Wii. A Wii is considerably cheaper than Xbox 360 or a PlayStation. So yeah, someone actually looked up the numbers, and turns out they're all around the same usage if you multiply by the number that is actually used. Yeah, this, I don't know what happened here, but this doesn't add up to 100. It has another problem, which is the false 3D perspective. Yeah, if you tilt any kind of chart to a false 3D perspective, certain differences are going to look larger than they actually are. So unless you're doing that for yeah, just showing what a shape looks like, you can't make any comparisons in fake 3D graphs. Yeah, this is also very tricky. It's very compelling to have a double axis figure, but you have to be very careful if you do that what you're going to show, and you definitely cannot cut both of them off, because yeah, everything will seem to correspond when you cut the axis to a certain starting and end point. Of course they will start at the same point, and then if they happen to go in the same direction, it looks like they correlate extremely strongly, which might not be an accurate representation of what's going on. Yeah, another, we don't even have an axis. And yeah, that's these ones. Okay, so what to take away from this? Cutting axis is fine, and you almost always want to cut off your axes, because what if you're measuring something that is somewhere up in the millions and it cannot ever reach 0? Why would you include 0? So you want to show the relevant area within the range of your data. So almost always you should cut your axes. But if you make a bar plot, if you're trying to show the height of something from 0, you shouldn't. Yeah, cherry picking, which happens in some of these cases, that's just plain fraud. So definitely don't do that. And double y-axes, they can be useful. But almost always it's better to show how two things correlate through regression analysis, which is what we're going to learn in the second part of the course. There are exceptions, like this one. I think this graph, okay, a bit crowded, but otherwise it's fine. Converting from Celsius to Fahrenheit is a linear transformation, so this is not two different axes, it just shows two different units of measurement. It's like meters and millimeters, there's nothing wrong with that. Okay, yeah, this is actually a nice article. It shows the effect of different ways to plot your data on how differences are perceived. So this is the actual data, and you can see that the vast majority falls into category A. Yeah, it's about 1/3, even more I think, maybe 2/5, maybe more. But if you tilt the graph, then actually it looks like A and B are more or less the same, which is yeah, very tricky. It's not true, and yeah, it is because a large chunk is taken up by this fake 3D perspective. So you almost never want to use these 3D plots. I think they're only standard part of Excel because it looks nice. But yeah, we're not trying to show nice things, we're trying to show the truth. So yeah, don't use this. Okay, if you want to read more about yeah, graphical integrity and also about graphical design principles, I really recommend the works of Edward Tufte. And also there's actually a pretty good overview on Wikipedia, which is just called Misleading Graph. And they show various ways in which data can be misrepresented. So yeah, if it interests you, you should definitely have a look. Okay, so yeah, how can you actually do it in R? I think that's the relevant part for this course. The first question is, why would you draw in R? Why wouldn't you just use Excel or Ggplot or Photoshop or Illustrator? Anyone have an idea for any of these four? Good point. Data is already in R. We've gone too far. But why not? Okay, you are right. Photoshop is definitely not for scientific drawings, but the reason is very important. When you try to make something artistic, the exact location doesn't matter. But when you're trying to accurately represent your data in a figure or in a table, then precision matters. So you shouldn't draw this manually because it's very prone to errors, even if you don't mean to misrepresent your data. Okay, about these other ones, Excel is yeah, very limited in the kinds of plots that you can make, and Ggplot is somewhat limited. Yeah, I think that any kind of proprietary software, it only shows you the kind of plots that they think that you are going to need, but you work in, yeah, in a very difficult field in biology, which is very diverse and very complex, so you need the flexibility that programming offers. You may need a very specific plot, and yeah, in R you can do that, and you don't even have to do it manually most of the time, because a lot of people write packages that can help you easily generate graphs that are commonly used in science. Finally, yeah, Photoshop and Illustrator, that's just dangerous, because yeah, and just like data cleaning, you can do data cleaning in Excel, you can remove values you don't trust, but then you're editing your raw data. It's really not a good idea. Also, copy pasting is dangerous. If you shift something one cell, then all your data are wrong. And the same with drawing. If you draw something in the wrong location, yeah, you are misrepresenting your data. So it's much, much better to do this programmatically, to automatically calculate where stuff should end up. And then any errors are only rounding errors due to the limited resolution. Okay, there are two yeah, main ways that you can plot in R. There are also many customized packages for specific applications, although in many cases they rely on Base or Ggplot. So what are the differences? Base doesn't require any installation. It comes pre-installed with R, and yeah, it doesn't require any functions that have been written by other people. It is a bit harder at first, and it tends to be a bit more verbose. So your code will get a little bit bigger, writing the same kind of figure. It has very poor defaults. I can demonstrate that right now. Let's say I want to plot the iris data set. Then a lot of the things I just mentioned aren't good are in here. For example, okay, it's a little bit small, but you can see that yeah, everything has a box around it. It's not really necessary, and it adds this effect where in the corners over here you can see moving dots if you look closely. Also, most of these plots aren't really relevant to what we're looking at, so why is this the default? Circles are the default for drawing points, but that is very rarely yeah, what you want to use. And also the default color scheme is not colorblind friendly. So can I do this? I don't know if this is gonna work, but let's try. No, okay, never mind. Anyway, just take my word for it, it's not very good. Okay, in Ggplot2, it will seem a lot easier at first, and we're gonna see that today, because if I told you to draw a map of coronavirus case in Base, it would be a very long evening. But in Ggplot, it only takes a couple of lines, and there are a lot of pre-written functions that we can use. It also has slightly better defaults, meaning that the axes are usually a little bit better to read. It adds a low contrast grid, which is sometimes useful, and it doesn't add a box around every figure, so that's better. You do have less control over the end result. Base is really the ultimate way to control every aspect of the figure. And Ggplot2 is a little bit more already set up for you, which means it's a little bit harder to move something to very specific end results. Okay, there is a very nice comparison that I will quickly show. And there's a point to be made here. So these are the default coordinates. Ggplot makes a low contrast grid, and Base will give you this coordinate system with a box and axes. I want to show several things. First off, the code usually, most of the time doesn't take much more or less in one or in the other. The end result usually is different in this comparison because there's no point in trying to reproduce one specific look in the other, because then first we have to define what looks better, and yeah, that's not very scientific. These are both fine graphs, but yeah, they both require a little bit of customization. This is what it looks like in Base, this is in Ggplot. Now, you can do most of the things that you can do in one, you can also do in the other. That's more or less the point that this guy makes in this comparison. I think this is very nice because it shows if you already know how to do something in Ggplot, then you can easily see how to do the things that he shows here. And if you want to know, well, I know how to do it in this one, but I have a package that relies on Base, so how can I do it there? Then you can see how that works. Okay, so, and that brings me to the first demonstration. There were two figures on the poster for the course. Let me see if I can quickly show it. Yeah, so these two. And we're going to be making this figure in R. I'm just going to show you what the code looks like. And I'm going to show you why I do the steps that I do. And then after that, I'm going to show you how you can do the same thing in Ggplot. So back to this one. And we're going to start with the base example. So yeah, this is the complete code. I'll make it a little bit bigger. And I'll make this a little bit bigger. Yeah. Okay, so I need one package for this. I don't really need it, but I really like this package because it can draw very nice axes, as we'll see. So first I'll show a very quick way to do it that doesn't look very fancy. What I do over here, this is just converting my data set from American units to SI units. And I need some colors because I think they look nice, but we'll do that later. First I'll show the simple way. I can just do plot and then height against girth. So this is the typical way that you would make something in Base. You specify what is the outcome and what is the explanatory variable. All models are also of this structure. So this will become the y-axis, the outcome, and this will become the explanatory one, the x-axis. And you have to specify where does it get this data from. So yeah, my data set is called trees SI because I converted it to SI units. Okay, so this would be the default. Some things I really don't like about this is that by default the numbers on the y-axis are rotated. It just costs a little bit more effort to read, and it costs no effort to turn them back. I think the circles are a little bit hard to see, and if you make them bigger, the circle gets bigger, but it's still not filled. And yeah, there's no reason to have a box around it. If you want to draw a line through your data, so you would fit a simple linear model like this. So it's the code I've written over here. And you can see that the model has almost the same code. Let me make a shorter name so that you can easily see it. Height as a function of girth, and the data set is trees SI. Actually, I can do this. It will still work. Yeah, so it's almost the same, and that's going to be a recurring theme throughout the course. The notation isn't that difficult because in most methods that we use, you can use the same thing. Also with the t-test, which we'll get to later. So how do I draw a line? Easy ways to do this, A-B line. So A would be the intercept, B would be the slope. And then I just say coefficients of my linear model. And there we have the figure. But yeah, if I want to add confidence intervals or prediction interval, we need a little bit more work. So that's what I'm going to show now. First, I made some colors. So this first part it tells me I want different margins and I want the numbers to be a little bit closer to the axes. This really isn't necessary. This is purely to make it look nicer in my opinion. So I'm not going to run this, and I'm going to show at the end the difference when I do run it. So here I wrote some code to create a transparent color. So here's transparent blue, and here's transparent coral, which is a kind of orange. And yeah, I made the data set, and then I have the plot. Now you can see for the plot I add a lot of customization. What do I do here? I remove the box, remove the axis, plot nothing, and then specify the y limit axis. That might seem a little strange. Why on earth would I plot nothing? This is all I get. Well, the reason is because I want to draw on top of each other. So if I add lines, it will draw on top of my data. And if I add a confidence interval, it will draw on top of what I already have. And a prediction interval, again, on top of that. And then I no longer see my data. So what I do instead is all the way at the end, when I'm finished, I re-add my data like this. Yeah, so it's all the way at the end. Yeah, so all this does is it creates a coordinate system because I'm going to draw on top of this. Right now I also use a B-line, but I say something else. I say a sequence from 0 to 50. Okay, so what does that do? It's a little hard to see, but it creates a little grid. Yeah, on purpose it's hard to see because the grid should be low contrast. Now, then I use this e-axis. You can see that I remove the axis in advance. Let's see what it looks like if I don't. These are the default axes. Yeah, I don't really like them very much. We only have a tick at 20, 30, 40, and 50. But if I use e-axis, so I'm going to set this to false again. Then it requires me to run this first. Sorry, so it's part of this package. Then you can see I have a large tick at 20, 30, 40, 50, but it also draws the small ticks, which isn't very distracting because they're shorter, but it does allow you to see a little bit more. So I like this function and use it a lot. And over here I say LAS equals 2. That changes the orientation to be horizontal, so all the text is easy to read. Yeah, and here I say one more argument, cex.axis. That is character expansion factor, and that means that I want the numbers to be a little bit smaller than the default, which is 1. So if I remove this, and again I make my plot, and my lines, and the axis, you see it's a little bit big, and I don't like that, so instead I do this, and I get smaller numbers. And you can also see what happens if you keep drawing on top of each other. It just adds. That's how base works. So every time, again, I start with plot and I run everything. I run everything up till here. So I run these lines, and it gives me coordinate system, axes, and a very faint grid. Yeah. Also note that we used the unit of measurement in the labels, which a lot of journals require, and it's always a good design choice. Then I fit the model. And I create some new x values. So I just create a very large sequence because I'm going to make a confidence interval and a prediction interval, and I want to add them to the plot. So I just say, okay, take all the values from 0 to 100, and then I'm sure we'll have enough. So I put that in a data frame. I make it first and then put it in a data frame. And then I say, add a prediction band. That is done with the predict function. Predict is very useful. It works for almost every model that we're going to learn in the course. You just say predict model, and then you say what you want to predict. So I want to predict the outcome for the values 0 to 100, yeah, with an interval of 0.1. That's what this part does. And if I predict and I say type of interval is predict, I get a prediction interval. So now I have the values 0 to 100, it's a very long list, and I get the fitted value for the data, and I get the lower bound, and I get the upper bound. So if I save that, and I then use another function Polygon, I can draw a polygon along these confidence bands, and see totally nothing. Let's see. Okay, yeah. I have to reinstall R on this computer, so the color doesn't work. We'll just use this one for now. But you can see that it drew a polygon along the prediction interval. Now, I can do the same with the confidence interval. So I guess this one also doesn't work. Okay, I'll just turn that into orange then. And then it will work. Yeah, so now we have a prediction interval which is wide and a confidence interval which is not so wide. And finally I add another one which is the regression line itself. And then in the last step I draw the points on top because of the intervals and everything I drew before, points were no longer visible. Now let me see, I think if I knit it, it will add the colors correctly because it's not using this graphics device. Yeah, there we are. So this is what it looks like with the actual colors I wanted to use. Yeah, this we'll get to later. But this is, more or less the result that you get. Does anybody know the difference between confidence interval and prediction interval? Because we see two different bands. Why do we have two different bands? Which one do you know? Okay, what's the definition?
The confidence interval is the let's say you can include all your points within a certain, like 95% of the time they will be in that interval.
That's the prediction interval.
Ah, okay, sorry.
Yeah, you can see that it holds true because almost all the points fall within the blue band, which is the prediction interval. So and I don't fault you for not knowing. Actually, there's been a lot of articles on this that a lot of scientists don't know the right definitions, which is why I hope to teach you in this course. But the blue band is a prediction interval. A prediction interval shows where do I expect 95% of my future values. So if I'm going to get more samples, more points, where are they going to end up? Now, a confidence interval shows something different. Why is it so much narrower? Anyone have an idea? It has something to do with that. So how can I estimate a line like this? What do I need to describe a line? How many things do I need to have? How many, at least? 2. You need at least 2 because I want to have 2 different things. I want to know how much it goes up and I want to know where it starts. Yeah, so I have an intercept and a slope for a line. Now, the intercept and the slope, so the anchor point is the intercept and how steep it is the slope. Both of them are estimated from the data. I don't know them. They are not with 100% certainty. So actually the starting point of this regression line, it could be a little bit higher, it could be a little bit lower in the population. And the same goes for the steepness of the line. I don't actually know that it's a dark red line. That's just the estimate from my data. But I have a limited number of observations, so I represent the uncertainty in the steepness as this curve over here in the confidence band. Yeah, so you can have R calculate that for you, but the interpretation of the confidence interval is what is a plausible range for my linear model. And the interpretation of the prediction interval is where do I expect my data. Yeah? We will get back to that more slowly and more detailed during the linear regression part. Okay, last steps that I do is I create a legend. I'm not going to explain everything in here. You can just Google R base legends and you will get a Stack Overflow result. But if I run it, you can see that it adds things over here. And it depends on the window size, so it's always nice to first knit your file and then see the results. Okay, before we get to the Ggplot example to show you how there are differences in the way you program that, I want to show one more thing, and that's this. these are called vector graphics. So the computer has a file in here that tells where to draw the lines. And that file is like a function. It shows like triangles, squares with coordinates, which means that it doesn't matter how much I zoom in, I always preserve perfect resolution. Yeah, so we have no problem with quality. You can also see if I zoom in on the text, everything looks great. And if I zoom in on the legend over here, everything is always crisp. Now, that's great, but that only works if you knit to PDF. So does anybody here use LaTeX? Okay, if you use LaTeX, you can use vector graphics. You can insert them into your file. Not all journals allow it because they can get very big. Yeah, if you do use LaTeX, you can have this very nice, very sharp resolution. If you don't use LaTeX, there's a bit of a problem. Let me see if I can show it. I am using a package to improve it, but we should still see a difference. Okay, so this is the same file, but now knitted to Word. I don't know what happened to the conference bands. I have to reinstall RStudio on this computer. Okay, why does it only zoom text? As you can see, I very rarely use Word. Let's just go to HTML. Okay, there we are. And I'm going to open this in browser and zoom in. Now, okay, it's actually not that bad quality. Why is that? Because I cheated. I'm already using this part which I said at the end that you should be using. So what I have to do to show you what it actually looks like when you do it is I have to go to Graphics and choose Backend Cairo, which is the ugly one. Okay, and then I knit it again. Yeah, so you can already, if I zoom in a little bit, yeah, it's hard to see because I'm using the whole page width, so it's still not bad. But over here you can see it. Maybe I'm nitpicking, but we'll see a better example in a little bit. The resolution of the text is getting worse. We have no anti-aliasing, and also these dots also look a little straight. It might be a little bit hard to see on this low resolution monitor, but that's okay, because I have prepared some examples. Okay, but before we do that, I'm going to show how to do the same thing in Ggplot. So I go to my other file, Ggplot2 Example, and I'm not going to explain every piece of code. You can have these files if you want, but I will show the differences in the way that you plot using base and Ggplot. Well, first, Ggplot is not standard in R, so I have to load a package to use it. And then the first steps, let me clear this up a little. First steps are more or less the same. Of course, I still have to convert my data because this was in inches and yeah, I want SI units, so I do this. And yeah, the model is still the same. And yeah, I still have to calculate a prediction band. Yeah, that's okay. And I create a new data frame. Now, here it looks very different. You can see that Ggplot works like this. I have a base Ggplot, I can run it. And it does this. It only creates this coordinate system. And here you can see what I mean by slightly better defaults than base. The text on the y-axis is horizontal, and we have a low contrast grid, which is nice in some cases. Now, and then I do a plus. And after the plus, I add an aesthetic element to the plot. I say theme minimal. That means I want a different theme. Okay, and then it has changed from dark light to light dark. And then I say add geom ribbon AES. Okay, let's see what that does. That acts the prediction band. So what's going on here? Geom ribbon, it means add a ribbon around something. AES means aesthetics. So why do they call it aesthetics? I have no idea. But yeah, better get used to this because every Ggplot works like this. You say what is your data set over here, and then you say my aesthetics are the y-axis, the x-axis and the y-axis. Yeah, so over here I say, okay, add a ribbon, y is upper, and then minimum is lower. And then, yeah, it should get from this stuff over here, which is the predictions, it should get the values to know the locations of the prediction bands. Okay, then we add another plus over here, geom_smooth. Now, this is a little trick. Ggplot has some nice features, which is why I said it's probably easier for you to learn than base. You will notice I have nowhere over here that I calculate the confidence interval. Well, why is that? Because Ggplot can do it for you. If you say geom_smooth and you say which method, it will try to compute the model and it will try to add a confidence interval. I just say standard error is true and I get my confidence interval. So it's that simple. Method lm means use a linear model, so it's the same one over here. And yeah, it does everything over here. I get the whole thing. Yeah, and the color dark red means the model, and fill coral, that is the color I see over here. You can also see I never have to say that it should be transparent because it already does that automatically in Ggplot. So the default settings in Ggplot are a little bit more beginner friendly and a little bit better. Okay, then I said plus geom_point. What do you think this is going to do? Yeah, add the actual data. Yeah, so now we're one step further. And then, well, what is Ggtitle going to do? Going to add a title. Etc. So this is the structure in which Ggplot works. You have your base coordinate system, and you say plus, 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 and you add all the elements that you want in your plot, which is very different than base, where you make something, plot on top of it, on top of it, on top of it. So this is like layers on top of each other, and these are like instructions, and only if I run all the instructions in a row do I get my end result. Yeah, you'll see there's no legend over here. The honest reason for that is that I'm not very good at Ggplot. I did find a solution for it, so if you want, you can go here. Let me quickly show it. And there's a little hack because, yeah, it's difficult to get a... that's what I said by if you want absolute control of your figure, base is a bit easier. Because when you use Ggplot and you add a legend, it is expecting that there are groups in your data. But yeah, I don't have any groups. I just want to say what blue and what red is. But they're not groups, they're just different bands. So yeah, you have to write a little hack to to have a combination of different legends. Yeah, but it can be done. Okay, so from this website that I recommend, again, if you want the slides, I can share them through Google Drive later. And then you can also access all the links. I can also put the example base and example Ggplot on Drive, and then it's easy to reproduce it. So what the guy said who wrote this page, and I agree with him totally, he says that, probably if you can do it in one, you can do it in the other. So people who say that one is better than the other, I can't really agree with that. Personally, I really like base because when it gets to plots, I'm a little autistic and has to look exactly the way I have in mind. And yeah, it just gives you a little bit more control. But if you just want to get it over with, you just want to graph, Ggplot is usually easier if you don't care too much about how the end result is going to be exactly. But both can be done in both. Now, if you're new to R, he says that probably what you should do is you should ask yourself, what are you trying to visualize? And then, go to a page, maybe look up the right kind of charts for the right kind of data, or maybe you already know I need a volcano plot, for example, or I need a spider plot, or I need a 3D pie chart, please not. And then just Google how to do that in R. So just do R volcano plot, R spider plot. And there are many nice examples out there, and all you have to do is edit the code so that it uses your data and your variables. And that's a much easier way to learn than to learn all the specifics of base in R and then decide for yourself which is better. And yeah, he also says, I agree, probably after the 5th or 10th example, you have used one much more than the other, and you're probably going to stick with that because you know it better. Okay, last part, before we get to the practical part, is graphics rendering quality. I'm going to show the problem using the default. So if you use PDF, there is no issue here because you can use vector graphics. But because a computer monitor or your printer or whatever, they all have limited resolution in the end. So yeah, your computer somehow has to convert exact coordinates to some discrete location. And that means a loss in quality, and we can minimize the loss in quality with some tricks like anti-aliasing. So for text, it's also a big problem, and that's what I'm going to show. Yeah. So the default RStudio device is called Cairo. So if you get any errors about Cairo, it means that the graphics device doesn't work. It works very well for PDF, but for PNG and bitmap, the default is not so nice. Here's an example. This was, if you render it to a lower resolution, we can really see the problems using Cairo. So it uses clear type. Anyone ever heard clear type or saw the setting in Windows? So clear type is a trick where if you know the resolution of the end result, you can use colors to make it a little bit easier to read from a distance. So it's like a special type of anti-aliasing. But here's the problem. You're probably going to resize your figure, use it in a presentation where it has a different size. And then if you, or someone is going to look at your paper and zoom in. And then these colors, they don't make any sense because they no longer occupy 1 pixel exactly. So clear type doesn't work for printed graphics and it is not a good choice. Then, this doesn't have any anti-aliasing, and here you can see aliasing artifacts. So, I didn't say to draw random shapes. I said draw circles, but at a limited resolution, those circles are going to look really weird. And the same with any kind of diagonal line or curve. It's going to have aliasing artifacts. And finally, here again we see clear type, but we see another problem called bad kerning. Does anybody know what that means? Okay, so kerning is the distance between characters, and the letter I takes up a lot less space than the letter G. So it should also have a lower space between the next character. So this white space over here is white space over here. This looks like you typed H space EI space GHT, and in a scientific journal, it doesn't look very professional to me. Also, the kerning here is wrong because the brackets are too far away from the M. Now, how can you fix it? First, easy fix is to just add this to every R Markdown file that you're ever going to use. What does this do? The default DPI, so dots per inch, which is a measure of resolution, is 72. That's just really low. For example, if you want to send something to a printer, they will usually say, or if you have to upload your profile picture somewhere, they will say we don't accept any pictures which are less DPI than 300. So if you set it to 300, it should in most cases look fine. Now this is very easy. You just have to copy this chunk and add it somewhere at the beginning of your R Markdown file. And what this says is it says options chunk set DPI 300. So that means every following chunk, every chunk after this, set this option, DPI is 300, so you don't have to keep typing it. Okay, alternative, just don't use the default device. There are other devices that you can use. For example, RAGG, which is anti-grain geometry, which is a really nice way to render graphics and much better than Cairo. And it's also faster, so if you make very complicated plots, or maybe there are some people here working with metabolomics data. You usually have a lot of data points, and then speed can actually matter. If you want to make 10 graphs on a slow computer, this is nice. And if you want to make one really big graph, even a fast computer is going to struggle. So speed can matter in some cases. How do you do it? You can just say install packages and then RAGG. That will install the package you need. And then this is what it looks like if you want to render a figure with RAGG. And you can see that everything is crisp, even though this figure is very low resolution. Yeah, it's only 720 by 720. Now, it might look a little difficult, like even more lines to add to my figures, but note that, you can just copy paste this for every figure that you're going to make, and the only thing you have to change is the actual plot. So the yellow part over here is what you would change to do what you actually want to do in R, and everything around it, it works the same for every other figure. You can also have the device in R, so that's the one over here, the one I have to reinstall because it doesn't want to print all the colors. Let's see, okay, I already deleted. And that's very simple. You just go to Tools, Global Options, and then you go to Graphics, and then you choose a different backend. So you can choose AGG. Now, and anti-aliasing, you can set it to default, which works well. The highest quality is subpixel, but it's also the slowest. So for very big figures, you might want to leave it to default. Yeah, and then all the figures that end up over here are no longer blurry. Okay, finally. Oh, okay, I spent a lot of time showing all the differences with this, but I forgot to add it to my presentation. So let me just show you the figures side by side. Oh yeah, I already put them side to side. So here's the differences. The top one is using the default Cairo, and the bottom one is using AGG. So yeah, you can see it no longer uses these strange colors that only work when every pixel is 1 pixel, but it just uses a grayscale anti-aliasing scheme. And yeah, anti-aliasing is so that when you have limited number of pixels, that if it should be somewhere, you know, there should be black here, but white here, but yeah, we only have 1 pixel, then it's going to be gray. That's anti-aliasing. Okay, oh. Not what I intended to do. Second one, you can see the anti-aliasing works very well because, yeah, circles now actually somewhat resemble circles, even at low resolution, and there are no more aliasing effects, which is handled very well by AGG. And finally, we can see that even the kerning issues are fixed because AGG is more powerful with rendering text in graphics, which is a complicated problem. You can see that the M is tightly enclosed in the brackets, and you see there's no more strange white space between H and E or between I and G because it knows that I is a smaller character and it takes it into account. Yeah, that one we don't need. Okay, so that was about 1 hour, which is nice because it means we have the next hour more or less to do the exercise. The exercise of today is from the crash course, the one called Specialized Graphics using Ggplot, where we're going to use these packages and then run this script to generate a map of coronavirus infections across the world on a given date. Now, and the exercise is to mess around with the code a little, show a different date, zoom in on a certain country, for example, and yeah, just see how changing the code changes the end result. What I'd like you to do is please try to install this so that if it needs to download anything that it can do it while you're having a break, and then after the break I can help you fix any installation issues. Yeah, so this is on the R crash course website. Are there any questions? Okay, then yeah, let's have a little 10-minute break and then we can do the exercise.